Good afternoon to all the participants. I am Devosri Sharkar, Assistant Professor from the Department of CSE, thrilled to extend my warm invitation for the International Short-Term Training Program in Machine Learning and Data Science Marvels, scheduled on 14th March 2024. This is the third day and second session, and the chairperson for this session is Mr. Sharup Kumar Hajra Chaudhuri. This session promises to be an enriching experience, offering invaluable insights and knowledge in the dynamic fields of machine learning and data science. I am honored to announce that Dr. Somnath Mukhopadhyay sir, Assistant Professor in the Department of CSE and Engineering at Assam University, Silchar, will be gracing our event as a distinguished speaker. Dr. Mukhopadhyay brings with him a wealth of expertise and experience evident through his remarkable contributions to the field. With a commendable portfolio comprising 48 publications, Dr. Somnath Mukhopadhyay sir work spans across the various domains, including but not limited to. We encourage to all the participants to who stay in the to stay with us for for this opportunity to interact with Dr. Somnath Mukhopadhyay sir and for and collaboration and knowledge and exchange that will undoubtedly enrich your professional journey. Welcome to our session, Dr. Somnath Mukhopadhyay sir. We are enlargedly waiting for our lectures today. And the Dr. Somnath Mukhopadhyay sir has completed his MTech and PhD degree from Kollan University. And now I am requesting to sir, please start your session.
Am I audible, madam?
Yes, sir, you are audible.
Yeah. Good afternoon, everyone. Let me share my screen. Is it visible? I have
Yes,
shared my
sir.
screen.
Yes, sir, it is visible.
Okay, so I will have 1 hour time to discuss on my topic, right? What is
Yes,
the
sir,
time
start
duration?
now and continue. You can start and continue, sir, no problem.
Okay, ma'am. Thanks. So today I will discuss an introduction to optimization algorithms. In this lecture, I will be discussing about what is optimization algorithms, why this is used, what are the different kinds of optimization algorithms. There are some benchmark or classical algorithms which are used for optimization, which are used for single objective optimization, and there are some algorithms which are used for multi-many objective optimization algorithms. So, optimization is a process of finding the best solution out of all available solution or out of all feasible solutions. The feasible means here the after applying the constraints, the search space becomes narrow, and within that space, we need to find out our optimization algorithm. In our daily life, we everyone encounter or we everyone witness many kinds of optimization. If we go for buying something, we thought of we uh, many parameters before buying something. So these all things are actually knowingly, unknowingly, we perform some optimization algorithms and act accordingly. So this is such a algorithm which is very much important in our daily life, which is also important for solving any computation problem. This can be used for searching, this can be used for anything for optimization. One classical example I can give, that if this is one mathematical example which we have studied in our higher secondary mathematics, that if y is a function of x, and if you want to find out the value of fx for a particular, or if you want to find out the max value or mean value of fx, and where that x exists, if you want to find out, then we can go uh, for that using some gradient based approach, which we have studied in our higher secondary, the principle of maxima and minima in that chapter. So if y is a function of x, and if dash x equals to 0, that means the first order derivative, if it is 0 at any point x equals to x star, then the optimum means either maximum or minimum, or the inflection point exists at that point. Inflection means the point where maxima or minima both are not exist. So a point x equals to x star, if there the first order derivative is 0, that means there is either maxima or minima exist, or neither of them is exist. So further, if we investigate, we'll find that the first non-zero higher order derivative denoted by n, such that if n is an odd number, then x star is an inflection point. That means there is no max or min available or present, or otherwise x star is a local optimum point. Here, local. This word is very important, because we'll discuss this, why this local word has come here. So further, if we again further go for this, if the value of the derivative is positive, then we are interested in finding the maxima or minimum value. So we have to investigate further. So if the value of the so our interest is not to find out whether there is no max or mean available or not. Our interest is to find out whether there is max or mean available, that thing. So if we again investigate this thing, if the derivative first order, if the derivative first non-zero higher order derivative is positive, then there exists local minima. If that is negative, then there exists maxima. Let us take an example. If fx equals to x square by 2 plus 125 by x, if this is fx, and if and the first order derivative will be x minus 125 by x square. So here the first x here the first, if we consider first order derivative fx equals to 0, and we will solve it, we will find that x equals to 5. So therefore the max or mean or inflection point is exist at this point, x equals to 5. Now again, if we derivative if double dash x means the second order derivative, we'll find that it is 1 plus 250 by x cube. So at x equals to 5, f double dash x equals to 3. So if we put x value in the second order derivative, we'll find that x equals to 3. The value is x 3, which is non-zero. So n is 2, and so total, so the local optima will be exist at the value x equals to 5. Since f double dash x equals to 3, and which is a positive number, so there is the minimum value exist. So the minimum value of fx, so we could find out that x equals to 5 is a position, is a point where the local minimum exists. If we now put the x equals to 5 value in the fx, in the original function, we will get 37.5 value, which is the minimum value of this function. So this is we have studied in our higher secondary mathematics. So this method can be applied for finding out maxima or minimum value, and which will give us local minima or local maxima, not the global minima or global maxima, because there can be many maybe local minima if the problem is a non-convex problem. If the problem is not convex problem means a problem which has only one minima or one maxima. That problem is known as convex problem. And non-convex problem means when there is many maxima or many minima, and those are actually local minima or local maxima. Now, out of which one will be global minima or global maxima. So the problem becomes complex, difficult, when the function is a non-convex problem. When there are many local minima or local maxima. So out of which we have to find out the global one. So that is a difficult task, and which we could not, it is not possible for us actually to find out that using this method. So we further investigate, or we research on this, and we find out if we use gradient principle, and means the principle of slope of a line of a curve, then we can also find out that this principle is actually used here. So we know that from our differential calculus idea, that the dy dx is a function of the change of y with respect to change of x. So this principle can be used to find out the gradient descent algorithm. And which is actually, suppose, just let me use my ms paint, and I can share you what is happening. So suppose this from this left, suppose this is left. So there can be this kind of straight line, there can be you know this kind of straight line, there can be this kind of straight line. So here three straight lines I have drawn, and which have different kind of gradient. So this function, the first straight line, is having the gradient equals to 0 actually, and here in the second one the gradient is positive. So because positive means because it is having some upstream here, and the third case the gradient is negative. So in these three cases, actually, now going back to our this gradient descent algorithm. So we want to find out the maxima or minima value. So if a problem is looking like this, that means this is a convex problem. That means there is only one minima, and this the point is here. If the problem looks like this, that means it has many minima values, or corresponding max values are also. So in this case, this problem is actually a non-convex problem. This is a convex problem. So in a convex problem, there are only one max or min exist. In a non-convex problem, there are many mean or max exist, and out of which one has to be the global one, and that is our interest to find out. So in these three cases, so using the gradient descent algorithm, we can find out which one is, or by what principle. So going back to your our presentation, so here if df dx equals to 0, so in the first case, so gradient is positive. 0 means that df dx is actually 0. So this is positive. Df dx positive means df dx equals to actually greater than 0, and the third one is df dx is less than 0. So this is the three cases we have considered here. So if df dx equals to 0, if that is the case, and if we want to find out the minimum value of fx, then actually what we need to do, so if we increase the x value, what is happening? Our slope is actually increasing. That means we have to decrease the value of x. You may have understood this. And if dfdx is greater than 0, and if we increase the x value, if x is decreasing when x is increasing, that means what? We have to increase the value of x. And if dfdx is greater than 0, but fx is at a max or min position, that means we are on a stable position, so we do not need to change the value of x. So in summary, we can decrease the fx by changing x But what amount? This amount. So delta x means the change of, so x new minus x old. So this is the delta amount which you are going to change on x is actually negative some eta value. Eta is the learning rate, and multiplied with df dx. So df dx is actually the gradient value. So when we are solving a problem of minimization, so the delta x is nothing but some negative value, negative eta value with the gradient value. So here eta value will be considered in the range of 0 to 1. So initially we consider a less value, a minimum value close to 0, and eventually when we are going at the end we are going to converge, we take a large value. So this idea, this is the gradient descent algorithm. This idea can be used for optimization, finding out minima or maxima. Of course, still it only can find the local minima, cannot find the global minima. So the idea is, let me draw one more thing. Suppose suppose this is my fx. Suppose this is my fx. This is the x. This is my y. That means the fx. So if we start from this point, suppose from this point, if we start, suppose from this point, if we start searching to find out the global minima. Suppose since this is a convex problem, so there will be only one local minima, and also that is only the global minima, because there is no more, no other global minima or local minima, and as well as global minima. So what is the here the gradient in this position? The gradient is what? Gradient is actually going to is having a downstream, so it's down. So that means the gradient is negative. So in this case, so we'll find out gradient at this position, and gradient we find that gradient is greater than 0. Sorry, less than 0. So in this case, actually, so since we are solving a problem of minimization, so our x bar, x dash, actually x dash, the next point, x dash will be what? X dash will be my some x dash will be my the old x value. So actually we want to reach in this position. That means we have to increase the value of x. So x minus the some small amount of change that we have to do, because since when x is increasing, my gradient is x is increasing, my fx is decreasing. So on that principle we have to actually, so there will be the eta and then the gradient dy dx. So this will be our, so here it will be x plus the eta with the this gradient value dy dx. So this will be the, so of my updated x value. So on that, using this principle, will reach here, and again we'll find out the gradient here, and again we'll move to the next location. So this is one kind of thing where my gradient is negative. If we start our search from here, in that case, what will happen here? Since the gradient is still here negative, but if I increase x, if x is actually increasing, on that case, my x bar will be what? X minus the eta with the df dx. So in this case, that way it will. So in that case, so the value of x will be decreased. So we will actually move in this direction. And the previous case, we had actually moved on this direction. So this is how a gradient descent algorithm can minimize, find out the minimum value of a function fx. So this can be actually one application I have considered here. This can be used to solve a regression problem. A regression problem means we have to find out there are there are some known data points, and along with that there are some corresponding y value. So we have to find out a best fit line, so that for an unknown value of x we can find out the value of y. So some data, this cross these points are some random points or some data set which are populated like this. and we have to find out a best fit line so that the error means sum of squared error, this function, the cost function, is minimized. So there can be many lines, and out of which that line will be selected which is best doing minimizing the errors. So the error is actually the distance between the this straight line points and with the original point. So the point on the straight line is actually my predicted point, and the point on the star is actually my actual point. So that the difference is the error. So y hat is actually my predicted value, and y is the actual value. And their difference is the error. So that we need to minimize. So here some 1 by 2m is multiplied just to when we will make the derivative part 2 will comes out, and then these two and these two will be cancelled. That's why this is used. So this is the cost function which you need to minimize through this in a regression problem. So regression is used for finding out the for prediction purpose, not classification. So here y is mx plus c is the equation of a straight line. Y m is m is the gradient, x is the data point, c is the y intercept. So C is the point where the straight line touches the y-axis. So if we consider the C value is 0, that means y hat equals to mx. So for different value of x, we'll find out a different value of y hat. And so just consider some different y values, sorry, x values, and that we have put in the function, and we could find out some uh, y values. So based on this thing, what we can do, we have considered different m values also. So m is the slope. Suppose the m is considered as point 0.1, then point 0.2, then point 0.3, then point 0.4. So different m values are assumed, and that for particular m value we will find a different straight lines, and those straight lines will give us some error, and that we have put in the cost function. So based on this exercise, if we put this in the right hand side this diagram, so for in the x-axis there is m, and in the y-axis there is a jm is the error. So if we use m value equals to zero point 0.5, we'll find some jm value. If we put m value 1, we'll get some error value. Error means jm. If we put m equals to 2, m equals to 3, different m values are used, and you know different errors have been calculated, and those are plotted here. Now we have got this kind of structure, this kind of graph. Now if we so now the problem becomes is to find out the value of m such that it gives us minimum error. From this diagram we could understand that this point will give us minimum error, minimum jm value. So that m value is actually my output. So when we could understand, when we could find out the value of m, x is the input. So we can easily find out the y hat value, the predicted y value. So based on this, we can solve this by using gradient descent, and we can find out the m value. So the convergence theorem is m equals to m minus the gradient value multiplied with some learning rate. So this is my algorithm actually. So that we have already discussed. So m equals to m minus. So when my gradient is negative, then it becomes multiplied on this becomes some positive value, and a small value is changed. Small fraction of value is changed. Then the value of the grade actually learning rate is changed. So m equals to m plus some small value. When the gradient is positive, then it becomes m equals to m minus some small value. So this way we can easily find out the value of m such that it gives us minimum error, and that will be the output of the the best fit line. So this way this can be useful to find out the to solve a regression problem. So this is an introduction about the optimization what is optimization, and how a classical approach can be used to solve this problem. So still there are problem. What is the problem? If the problem is having a curve like this, in that case there are many local minima, and which we cannot solve using gradient descent algorithm. And also, so if there are many basins like this, we cannot solve this problem using gradient descent, because gradient descent will stop here, will not, it will find that this is the minimum point, so it will not go beyond that. So if we start searching from here, it will stop it here. If we start searching from here, it may stop here. So this way a non-convex problem cannot be solved using a gradient descent algorithm. So this is one disadvantage of this. Another disadvantage is, uh, the the function has to be differentiable, otherwise we cannot apply gradient descent algorithm. So if the function is discontinuous, then there will be some points where differentiation is not possible, derivative is not possible. So in that case, we cannot use this algorithm to solve this kind of optimization algorithm. So to solve such things, we have to go beyond this, and there are solutions which can solve this. So now I'm going to discuss genetic algorithm is a solution to these issues, which can find out, or which can solve a non-convex problem, which does not use gradient approach. So the function has not to be, there is no need of there is no need of you know there is no need of the function is to be differentiable. So this way, this algorithm, genetic algorithm, is very much powerful. Still, in today's research, also genetic algorithm is used, by. So, what is the history of this algorithm? Or what is all about this algorithm? This is a randomized search algorithm. Means this algorithm inspired by our biological evolution process. These algorithm can also be called as a nature inspired algorithm. This algorithm uses the concepts of natural selection, genetic inheritance, survival of the fittest. So these concepts, which are present in our real life, will be followed here. So the natural selection means the selection of the solutions are done in random, and the parent from parent to child, the property inherits. And there is another principle, survival of the fittest. The solution which has better fitness will survive, and the solutions which are not that kind of fitness value can will be eliminated, or cannot will not be able to survive further. So it was developed by John Holland in 1975, and since then it is widely used by researchers, and in today's research also it is used. So why GA? Yeah, this is in our real life. If we think that our daily life, there are many problems in our many problems which are you know based on optimization algorithm. And in our real life, most of the optimization algorithm problems are actually not solvable in polynomial time, uh, because there are no such deterministic algorithm exist. If we consider the problem of traveling and salesman problem, or knapsack problem, or Chinese postman theorem. So there are many algorithms which are not polynomial time algorithms. So on those cases, we cannot solve those problems in polynomial time. So maybe if we solve traveling and salesman problem, one salesman is traveling many cities exactly once with minimum cost. If there are 4 cities or 3 cities, Then there can be paths like A, B, C. If the cities are A, B, C, so A, B, then C, or A, then C, then B, or B, then A, then C, or B, C, A, or C, A, B, or C, B, A. So only for three cities there are six different possible paths. So, and getting, enumerating all paths and then finding out the minimum, cost path is a troublesome problem, is a non-polynomial time problem, because if there are 50 cities, we cannot enumerate all possible paths and then find out the minimum one. It's not possible. So these problems are NP-hard problem. So in these, since these problems are not solvable in polynomial time, so we have to use some, other approach. We have to follow some other approach to solve this kind of problem, so that we can solve this problem in polynomial time at the cost of, compromising some sort of, accuracy. Suppose a problem which can be solved in some direct approach or deterministic approach, or brute force approach, means enumerating all possible paths and then choosing the best one. Suppose this takes 10 days of time in our modern computer, and there is another algorithm, suppose one optimization algorithm, genetic algorithm, which solves this problem in 10 minutes, but it solves this problem with an accuracy of suppose 99.999%. So we should choose the solution which is coming from genetic algorithm in very less time compared to the previous one, at the cost of some sort of, accuracy. So still this problem is chosen because of time complexity. So this is one reason. Another reason, when the problem can be modeled as an optimization problem, then we should use genetic algorithm. Efficiently searches for global optima when multiple optima exist. That means when the problem is non-convex. Parallel implementation easy means there are some components which can be solved in, in parallel with other or simultaneously. So one diagram you can see here, there is in the x-axis there is many problems, set of problems, and in the y-axis there is efficiency. So there is a problem P, one problem P. We can see that one specialized algorithm performs very good for the problem P, and there is a, from the curve you can understand this. And compared to that, there is the red colored last curve, which is actually genetic algorithm, which is performing very good, or performing very better compared to the specialized algorithm for all the problem sets. But the problem P, it has a marginal, less accuracy compared to that. So here we can see genetic algorithm is performing good over a wide range of problem, and the specialized algorithm which is performing best for a special problem. So this, for a special problem, this specialized algorithm can perform better, but genetic algorithm can be used for many problems for a wide application. So this is the strength of this algorithm. So it has some features like the search and optimization technique is performed based on some evolutionary, approach. It follows principle of evolution, survival of the fittest, and inheritance. This is part of that. It starts with encoding of the parameter set. It searches for a population from points. It uses probabilistic transition rule. Going through this, so it has direct resemblance with the nature. It follows the rules of our nature. What is happened in nature. Genetic algorithm actually follows that. So it has some stochastic operators like random operators, selection, crossover, and mutation. These are all random operators, which performed based on some random operation. The quality of the solution is judged by the fitness value. The The solutions are represented in terms of gene, and many genes when combined it is known as a chromosome, and a chromosome is actually one solution. So one candidate solution is actually one chromosome which has the component, uh, I mean the smallest part of a chromosome which is further not visible is known as genes. So how it performs, how it works. It starts with initial population, produce an initial population of individuals. It starts with that. For initial population is encoded randomly. Then we find out the fitness of the chromosomes. So a population means a set of solutions. One solution means one chromosome. So one population means set of solutions or set of chromosomes, and chromosomes are made using genes. So evaluate the fitness of all individuals there are some then until and unless termination criteria met, we actually performs the stochastic operations such as selection, such as crossover, such as mutation, and then again we calculate fitness. And when we go back, if the fitness is satisfactory, you terminate, or otherwise again it reiterate this. So perform selection to create mating pool. So from mating pool, crossover and mutation happen. So select there are many kinds of selection operators, so which will be used to perform which chromosomes are good, which chromosomes are bad. So that thing is known as selection. So encoding is done in random fashion. Usually it is encoded using binary strings, zeros and in terms of zeros and ones. There can be real numbered GA as well. That is also possible. So if L is the string length, the number of different chromosome possible is 2 to the power L. So it's very obvious. Population is set of chromosomes in a generation. Population size, I have already told these things. Population size is usually constant, means 20 number of chromosomes, 30 number of chromosomes. So common practice is to choose initial population randomly. So suppose we want to solve a problem f(x) equals to x into 8 minus x. So this is one function of x where x is in the range of 0 to 8. So if we want to find out the max value of fx, how can we do that? We can solve this by using genetic algorithm here, but in our common sense, what we will do, we will put different x value and in different in the fx. So we'll find out f0, f1, f2, f3, f4, f5, f6, f7, and f8, and which one gives the max value answer is the answer of the problem. But these problems become completely a different kind of problem if we consider the x values, suppose up to 4 decimal places. So the first x value is 0 and the next x value is 0.0001, and the next one is 0.0002, 0.0003. This way, if we consider these x values in the range of up to 4 decimal places, this problem becomes extremely difficult. And though it is in the range of 0 to 8, but it becomes a infinite. So on that, this way, this problem cannot be solved by using some direct approach. So here we have used genetic algorithm to solve this problem. Here the solutions can be thought of some using some binary string. Suppose solution is like 8-bit representation. So one 8-bit representation like 100110101 random solution. So this is one solution. If we consider these as a solution, so this has a corresponding decimal value, and that decimal value is actually coming in the range of 0 to 255, because one 8-bit representation can give us solutions in the range of 0 to 255. So that 0 to 255 value, which from the binary string we are getting, has to be converted to 0 to 8, because that is our original string length, I mean X range. So 154 value is actually mapped to 0 to 8 by this simple formula that we can use. So now this X become 4.8313. So using these, so different solutions, different chromosomes of suppose the population size is 4, that means there are 4 chromosomes. So 4 chromosomes having corresponding decimal value, and that decimal value is again converted to the X range. So that is 4.8, 3.2, 0.6, 5.8, this way. If we put these X values in the Fx value, we will get a fitness value. So that is the fitness of the particular solution of a particular chromosome. So out of these 4 solutions, which one is best? The best is will be must be 15.40, since we are solving a problem of maximization. So the X value 3.2 gives us better result out of these 4 solutions. So now we have to use. So after chromosomes are evaluated for their solutions, we have to based on their fitness, we have to find out which chromosomes will be selected for going to the mating pool, which are not, which are so we'll follow now survival of the fittest, that principle, the principle of Darwin. So selection is more copies of good strings are selected, fewer copies of bad strings are selected. Proportion selection scheme. So one selection algorithm is Rowlett wheel selection, or there can be other selection algorithm like Rhodaman selection. These are widely used and these are popular. So the example of Rowlett wheel selection. Suppose chromosome 1 is having fitness 15.30, because if we put 4.8 in fx, it will give you this 15.3089, this value. For 2, chromosome 2, this value. Chromosome 3 is 4.8363. Chromosome 4, 12.397. This way, we have the fitness of the 4 chromosomes. Now, Rowlett wheel means there will be one wheel, and that wheel can be spinned, and there is a pointer which is pointing to the wheel, and if we spin the wheel, after some time the wheel will stop after spinning, and the pointer where it is pointing to, and the chromosome, I mean the numbered part of the wheel will be selected, and which will be the I mean the chromosome which is selected for the going to mating pool. So this way here, if we perform cumulative sum of these 15, 15.4, 4.8, we'll get some, we'll get some total value. And then if I divide by the cumulative sum, is actually the amount of space in the wheel, or the proportion in the wheel. So here 15.30, maybe chromosome 1, it has got this amount of space, chromosome 2 is having this amount of space or occupancy, here chromosome 3 is having this amount of occupancy, chromosome. So this is very simple thing. Now just we are making cumulative sum, and the percentage of area which it covers is actually taken into this. So now, since there are 4 chromosomes, we'll spin 4 times. If there are 20 chromosomes, we'll spin for 20 times. Suppose spin one, chromosomes 2 selected. So 2 has been taken into the mating pool. Again we spin, again one chromosome has come. Again we spin, again one chromosome has. Everything is randomly. So this is our mating pool which we have got after Rowlett wheel selection. This is the logic. So this Rowlett wheel selection has a disadvantage that it can select the worst chromosome also. So that is one, because this is kind of lottery. There is kind of lottery. So there is a chance of also selection of chromosome 3 can be there. So this is one disadvantage. To overcome this, you can use binary tournament selection, ternary tournament selection. Tournament selection means this is a knockout kind of thing where true chromosomes are randomly selected, and the best one out of between the two are selected for going to mating pool. So this way, it guarantees that the lowest fitness value chromosomes will never be selected or copied into the mating pool. So this is another kind of thing. The next operation which comes as a crossover algorithm, which is actually a recombination operator, which is a probabilistic operation in our real life also. Not every parents go through crossover or recombination or reproduction. So, but there is a high chance of this operation. Maybe 90% chance is there to of crossover. So it is how what is the concept of this? It is exchange of genetic information. So two parents are selected randomly. Suppose this is one parent, this is another parent, which are randomly selected from my mating pool. And now whether we should perform crossover or not, we can do one thing on probability check. We can generate one random number using a rand function in MATLAB, and if that number is, suppose if we consider crossover probability is 90%. So if the number is between 0 to 9, we can perform crossover, and if the number is 0.921, then we will not perform crossover. So this way we can perform this probability checking. So there can be many kind of crossover operation, single point, uniform, multi-point, many things. That this is one example. This is one parent. There is another parent. Suppose one random location is chosen randomly. Uh, Suppose the string length is and k, the crossover point is selected as randomly 5. So this is, since this is only genetic exchange, information exchange between the parents. So this will generate this as a children, two children are this. So from the existing solution, actually, what is the need of this? From the existing solutions, we are actually generating new solutions. So from parents, we are generating children, next generation solution. So there can be many kind of crossover algorithms. I'm not going through this. So this is one uniform crossover algorithm. You can generate one mask randomly. When there is a one, you can exchange their genetic information, unless not. This way this can be done. So there is another probabilistic operation, stochastic operation in genetic algorithm, which is known as mutation. Mutation is actually having very less probability. Mutation is performed. Mutation is the strength of genetic algorithm because it overcomes or it provides the solution to to get rid of genetic stuck in local optima. So some random alteration in the gene can produce a new kind of solution, and that is very much important in during our search space. So crossover is actually known for exploitation. What you have in your hand, you just exploit that. Use those things, making some manipulation and try to generate new things. That is exploitation, which is actually crossover operation performs. In case of mutation, what is happening? What happened? It generates a random alteration and it provides new solutions, and it actually helps to go beyond our search space or our local search space, or it finds new search areas. That's why it is known as operation of exploration. So one is exploration, mutation, and then exploitation means crossover. So how it is performed? It is also probabilistic. So it is a unary operation. One parent is chosen randomly. So when there is a probability pass, we perform 0 to 1 and 1 to 0, like that. So for every bit, we check whether there is a need of performing mutation or not. To do so, we have to generate a random number. Suppose the mutation probability is 5%. So in that case, if the generated random number, suppose in between 0 to 0.05, then we perform mutation, or otherwise from 0.05 to 1 value will not perform mutation. So that's how. So the mutation occurs. So there are these are parameters: population size, string length, probability of crossover. These are user supplied parameter. Termination criteria: when you will terminate, either after 100 iteration, 200 iteration, or you will observe the base chromosome of every iteration, and when you are finding out that there is a no change in the uh, in the solution, that means you can terminate there, or you can stop it there. So this can be some example of parameter set. So this I have already discussed. A cycle of selection, crossover, mutation. Okay. So there is another concept which is known as elitism, which is also used in genetic algorithm. Elitism means, uh, since it is a random operation, so sometimes we find a very good solution, and when it goes through crossover or mutation, that solution may be altered and we may lose that. So to protect this, what we can do, we can save that solution, the very good solution, out of your population, and in the next iteration you find out the worst chromosome, and you cross check. If the worst chromosome of the next iteration is better than the best of previous, you can replace the worst of this with the best of previous, or you can continue with the worst one. So this is elitism, just not to lose the best solution. This is one. So this is a single objective optimization algorithm, where we can use genetic algorithm as a solution. Now I am going to discuss the third slide, which is actually where we use multi-objective optimization algorithm. Here also we'll consider MOGA, multi-objective genetic algorithm, to solve multiple objective function. So multi-objective optimization algorithm problem is MOVE. There, the previous one is SOP, single objective optimization problem. So multi-objective optimization problem means when there are many, more than one conflicting objectives. That means if you want to, suppose you want to go to Guwahati from Silchar, so you'll find many kind of transport. So just let me give one example. This one. So which car you're going to buy? You're going to buy BUY. The spelling is wrong here. BUY. So which car you will buy? Mercedes Benz or Tata Nano? Which one you will buy? So, so this is a problem which is actually solved using multiple objective function based on that. So which one is more important for you, cost or comfort? If you are not, you know, uh, worried about cost, why you will buy Tata Nano? If you are worried about cost, then why you are buying Mercedes Benz? You cannot do that. So So cost, cost and comfort is actually conflicting with each other. If we invest more, you will get more comfort. If we invest less, you'll not get that amount of comfort. Conflicting objectives. So simultaneous object optimization of conflicting objectives is the principle of this, is the logic of this. So what happens actually? Improvement in one objective causes degradation in another objective. That actually happens. Most of the real life problems are multi objectives in nature. So there is another example. So there are many kind of transport type. So in x-axis there are many transport kinds type, and the x-axis there is economy level, and y-axis time taken is given. So if we go somewhere by walking, there will be very less in the x-axis. You can see the x value is very less, so economy level is less, but time taken is very high. If you use bicycle, it is faster than walking, but it has higher what higher economy level, but X value is increasing. If you use horse, it has a more higher economy level and time taken is less. So if we are thinking about time, then you have to invest in, we have to compromise economy. If we are thinking about economy level, then you have to, you know not think about the time taken. So there are these kind of, so rocket can go faster, but rocket is expensive. Aeroplane, then scooter, I mean bike, these things are there. So there are, so all these are different solutions for as a transport problem, as a transport type. So there are two cars. You can see here this car and this car. These two car is actually having same economy level. You can see their economy level is same, but their time taken is different. So when one objective, the economy level they are same, but time taken is different. Here you can choose which one is best among these two. So here the red arrow part is having much larger time considering compared to this black car, the green arrow car. So between these two solutions, these two car, the green arrow car is a better solution compared to this. But you cannot compare one car with one motorcycle, or the car with the horse, or horse with the bike, because they are having different economy level and different time taken. So these all solutions are non-dominated in nature compared to other. So in a single objective optimization problem, we optimize one function fx. In case of multi-objective optimization algorithm, multi-many, actually there can be, there you have to think for optimizing many functions f1, f2, f3, fk. So with some subject to constraints. I'm not discussing this. So two things are there. One is objective space. The x values are plotted, and that plot is known as of variable space. And where fx is plotted, that thing is known as objective space. So one is variable space, and another objective. These two things are very much important. So if we minimize x square comma x minus 2, then there is two function. F1 is x square, f2 is x minus 2 whole square. So here x is actually the decision variable, and that's why x is the variable, and x square and x minus 2 whole square, these are the objectives, and these are objective space, plotted in objective space. So here there are two goals to optimize. One is to progress mm, towards Pareto front. Means Pareto front means the solutions, that solution. So this is known as a front. This is a front. Front means a set of solutions. Set of solutions. So here in this solution you can see this is one front where this standing person, the bicycle, the horse, the scooter, I mean the bike, this car, this aeroplane, this aeroplane, this I mean the helicopter, aeroplane, and the rocket. These all will come in the front. So this front is actually my front one. That means this front one is having solutions which are not dominating with other solution. So no solutions can dominate other. But in this car is, since this car is having less, a higher, time taken when economy level is less, this will become to the rank 2 solution, means front 2 solution. This is the concept of front. So dominations, what is dominations? A solution x1 is said to dominate a solution x2 when every objective of x1 is not worse than x2, and there exists at least one objective for which x1 is better than x2. The meaning is, so for every objective of x1, for example, there are two objective function f1 and f2. So for every objective means f1 and f2, x1 is not worse than x2, and there is another objective function, suppose f3, for which x1 is better than x2. So in that case, we can conclude that X2 is better solution than X2. So X1 dominates X2. So where Fi X1 is a solution. So Fi one fitness function Fix is strictly less than this. So not odds. Less than equals to means not odds. And there is a I exist from the 1 to k such that f of x1 is strictly less than f of x2. So there is a equal to part, and this is inequality, and this is the this is the beauty of this thing. So here from this diagram we can see blue balls dominates red balls. Why? The blue balls has a less x value than the red balls, and blue balls also having less y value than the red balls, but green also dominates the blue one because green has this green is inside this box. So green dominates blue, and this that is why green is better solution than the red blue one. But blue cannot dominate the gray one because why? Blue is having, suppose you choose this one, you choose this one. So this blue is having less x value than this gray one. Suppose so this, and this gray is also cannot dominate the blue one. Why? Because the gray is having less y value compared to this blue one. So that is how they are non-dominating with each other. So a solution is Pareto optimal if no solution can dominate it. Set of Pareto optimal solutions point in the variable space is known as Pareto set. Set of all Pareto objective vectors is known as Pareto plot. Just I have told you this thing. So here these blue balls, when they are connected, they form the Pareto optimal front. And this front actually dominates these balls, these hollow balls. So these are some example. When the problem is a mean problem, means you are trying to minimize f1, you are trying to minimize f2. So this position, this area is actually your area of non-dominant front one solution or Pareto front solution. This way, when the it is a min max, this location; when there is a max min, this location; when there is a max max, this location. This way, this will be changed. So every optimization problem can be converted to a minimization problem. I mean, maximization problem can be converted to minimization, or minimization problem can be converted to maximization, because there is a concept of duality. No, so if you want to minimize effects, I mean maximize effects, so that actually is equivalent to minimize minus of effects. So maximization of effects is equivalent to minimization of 1 by effects. So this way, this is there exists some duality. So goals in optimization algorithm is convergence to the Pareto front. So go reach as close as to the Pareto front. This is one goals, that is known as convergence. And the another thing is divergence. So well diverged solution is always desired, or is a better solution. So when when the problem is a multi-objective optimization algorithm or multi-objective problem, so there will be multiple solutions. So the when multiple solutions means we have to generate as many possible solutions in the Pareto front. So then that means the front becomes white. The spectrum becomes white, and that is acceptable by the community. So if I am solving a problem of, suppose, optimizing portfolio, portfolio means if you have 100 rupees of money and you want to invest that money in the stock market, so which are the stocks where we need to invest such that you get maximum return, and with subject to minimization of the cost, I mean the loss. So there is a return and there is a risk. Two things are there. So if I'm a fund manager, and I recommend, or I give suggestions to the customers who want to invest. So there can be many different customers. Someone is having 1,000 rupees to invest. Someone is having 1 lakh rupees to invest. Someone is having 10 crores of rupees to invest. Someone may have billion, trillion amount of money. So I should have solutions for all these kind of customers. I should not deal with only one customer. So one solution means that is acceptable for a particular kind of customer. Another solution is acceptable for another kind of customer. So the well diverse solution is always acceptable and is a better solution. So well diverse is that is how it comes into our consideration. So cover the whole spectrum of Pareto fraud. That is the thing. So properties here, green is a good solution because it is a very wide, very close to this line. So it has convergence. It is maintaining convergence. It is maintaining divergence, convergence and diversity. Here, blue, the red balls are bad solutions because it is not that close to the Pareto true Pareto optimal front, and it is also not having that kind of wide spectrum. This is very classical approach, weighted sum method that I'm not going to discuss. I'm going to discuss directly. So there are many MOGA because many researchers have developed their own kind of MOGA algorithm, Vega, MOGA, NPGA, NSGA, many algorithms are there. I'm discussing the most popular one, which is known as NSGA-II. So there was NSGA, and then NSGA-II is proposed by Professor Kullanmoy Dev in 2002. This paper is having more than 53,000 citation. So from this we can understand the power of this algorithm. So it is a population-based algorithm. It is macrogenetic, not uh, you know. It is generational. It follows elitism approach. How it works? It starts with some parent chromosome PT. From there, it generates a QT by some selection, crossover, and mutation. Then, so PT, if PT is 20, QT is also generates as a size 20. So by union, it becomes 40 size of chromosomes. Then the 40 size, we remove the 20 and best 20 is selected to go for the next iteration. So here we perform first non-dominated sorting. NSGA means non-dominated sorting genetic algorithm. So here we perform the sorting part to choose which one is best. So sorting is performed because of to understand or to maintain the Darwin's principle, the, the best one should be selected, uh, survival of the fittest, that principle. Then crowding distance, there is another concept which is followed, and then the next iteration is calculated. So I'm going to directly the sorting part. The other things are very simple. So here you can see blue dominates red because blue has a less X value, blue also have a less Y value. Green dominates blue, green has a less X value also compared and the also Y value. Blue cannot dominate gray because blue has a higher X value sometimes and blue has a higher Y value sometimes. And gray cannot also, vice versa is also so. So this is this. So how the how the sorting is performed? This is the sorting algorithm. Yes. So here PT is suppose there are four solutions and the gray balls or white balls, and there are four solutions in QT, which is actually made from PT by crossover, mutation, selection, those things. So there are now eight solutions. So PT and QT, when they are union, they generate eight solutions. So we need to select the best four. How? So here we consider two things. One is S1, one vector S1, and there is one scalar value N1. What is S1? S1 means solution 1 dominates which solutions? So S1 means the set of solutions which are dominated by solution 1. So here solution 1 dominates which solutions? It dominates 5, it dominates 8, 4, 7, 3. These solutions. And there is another thing. So S2 is actually set of solutions which are dominated by the solution 2. So solution 2 here dominates which solutions? Solutions 3 and solution 7. And all other solutions are actually having less x value to S2. So this way this is calculated. And there is another scalar value which is N1. N1 is here is if S1 is a strength, you can say N is the weakness. So here N1 means which solutions can dominate the solution 1. So N1, if N1 is here, N1 is 0, that means there is no solution which can dominate 1. N2 is 0 means there is no solutions which dominate solution 2. Here N3 equals to 3 means solutions 3 is dominated by how many solutions? By solution 2, 6 and 3. That means N3 is 3. This way this is first done. And according to the value of n, we choose which solutions will come as a front-on solution. So here n1 is 0, n2 is 0, n6 is 0. That means these are the solutions which are not dominated by any solution. So they are coming under rank 1 solution. So when 1, 2 and 6 mean removed from consideration, so the rest of the solutions are considered, and out of which the rank 2 is made, and from there rank 3 is there. So this way the sorting is performed. So there is another concept which is known as crowding distance. Crowding distance means a solutions, if located in a quotes position, quotes location, or in a crowded location, that means then that solution is having less crowding distance value, CD value. When a solution is very isolated, then that solution is having CD value highest. So the concept is to keep those solutions whose CD value high. Actually, the logic is to make our spectrum, I mean the Pareto front, white. So one solution who has higher CD value is considered to be a better solution than a solution whose CD value is less. So this way, this is calculated. I can, if you are interested in discussing these things more, you can contact me later on after this discussion. That can be helpful, because then we can use some more realistic example, or we can consider some problem to discuss these things in more detail. So how this selection is done? So we have our ranking information, we have our crowding distance information. So I dominates solution J. If I rank is less than J rank, then directly they dominate. So there are some solutions which are first rank solution. So the first rank solution always dominates rank 2 solution, second rank solution. Or if their rank is same, when two solutions are located in same front, then which solution is good? Whose crowding distance is high? That solution is chosen as the better solution. So this way the solutions can be selected as a better or worse. So convergence and diversity, these two are the measures by which we can understand. So there is one performance matrix that is known as hypervolume that can be used to find out which solution is having betterness, or which solution is having better in terms of convergence and diversity by using this hypervolume. So when there is a single objective of measure, then it becomes area. When this is multiple objective, when it is two objective, it considers area, and when it is more than two, it becomes hypervolume. So this way, I think I have no more time to discuss. I can have questions if you have. Uh,
Hello.
describe. Thanks for your
Hello.
and yes, please.
Hello. Thank you, Dr. Shomnath Mukhopadhyay. And first of all, how are you? Hello. Am I audible?
I can hear you. I can hear you. Please.
After a long time, actually. That's why I'm asking you. How are you?
I'm fine. I'm fine.
Okay, okay. Can
Whatever.
you guess me
We'll
actually
we'll
who am
talk.
I?
We'll talk later on. Yeah.
Okay, okay. Later we'll be talking about that. So there are so many questions. As our discussion draws to close, I want to express my heartfelt gratitude to our esteemed speaker, Dr. Somnath Mukhopadhyay, for his enlightening and thought-provoking insight. It has been a truly enriching experience to hear his perspective on topic optimization algorithm. Before we conclude, I would like to pose a few questions to Dr. Somnath Mukhopadhyay to further deepen our understanding of the topic. So there are so many questions. So I have chosen some few questions from them. Can My first question is that to Dr. Mukhopadhyay, can you propose a modification or an enhancement to the standard gradient descent algorithm that could help it escape from local minima and coverage to the local minimum more effectively?
No, there is no such solution, or we cannot overcome the limitation of gradient descent algorithm. And that is the reason we should use these global optimization algorithms such as genetic algorithm or PSO or end colony optimization. So by using gradient descent, will always stuck in local optima. One solutions can be that we have to make different trials and we have to start our search from different location. And if we try for suppose 50 trials, and out of which one time we can find out the global optima.
Okay.
So just trial and error can be one solution. There is.
Yeah, yeah. And there is another question that is from also from audience. Discuss the potential trade-off and challenges associated with implementing your proposed modification. How might it impact the coverage, speed, and computational efficiency of the algorithm?
The computational cost of genetic algorithm, is that the question?
Discuss the potential trade-off and challenges associated with implementing your proposed modification. Means, if you want to propose
No,
the modification, then the
today whatever I have
potential trade-off and
discussed,
challenges.
today whatever we have discussed is actually the classical
I
algorithms.
think it is related to the challenges and potential trade-off.
The
Okay.
challenges,
Yes.
the challenges can be. That is why there are some hybridization models are there in the literature.
Yeah.
So there are some. Suppose there are some limitations of genetic algorithm. Suppose genetic algorithm is not good at local search. So
Yeah.
where PSO is having good at local search. So the genetic algorithm is good at global search. So genetic algorithm and PSO, if we can hybridize, then genetic algorithm will perform very good at global search by using the mutation principle, and PSO will perform good at local search because PSO is having the distance from local based, I mean the P based and global based. So PSO GA, if we hybridize, then the algorithm will be more powerful compared to a classical genetic algorithm, or also compared to classical PSO algorithm. So there are these kind of shortcomings which are not much very important to discuss, because these all algorithms are very much powerful. They can solve uh, all all general problems, all general set of problems. There can be one algorithm, one problem for which a particular algorithm performs better, but for as a wide range of problem, if we consider GA, PSO, these all performs better.
Okay. And there is another question. What is the utility of genetic algorithm?
Utility means applications, right?
Yes, yes, applications.
I have given you here one example of traveling and salesman problem,
Yes,
or
I saw. Actually, that is coming from audience. Another question. I'm directly going to another question. I think it was already
or
discussed.
also in image segmentation, or more in general example, in image segmentation, if we use a thresholding based approach for image segmentation.
Okay.
So initially we choose some, some random points as the solution, and next time we reiterate to find a better solutions of the threshold values. So in that case, we can also use genetic algorithm for image segmentation,
Yeah.
or there can be, suppose there is one neural network and where the weights has to be optimized. So GA and a neural network can be hybridized to find out the optimal weight set for the neural network. So
We can we
GA can
can
also be yeah, GA can also be hybridized with fuzzy logic, so or fuzzy algorithms or fuzzy controller. So there are some limitation of fuzzy algorithm which can be overcome through genetic algorithm. So all these algorithm has their own beauty, and that can be leveraged or with hybridized with other algorithms to make
yeah.
it more powerful, more strength like that.
Okay. There is another question. Can genetic algorithm be adapted to different types of steganographic technique, such as spatial domain or transform domain method?
I am not much aware of steganography, so
Okay.
I'll not be able to answer this.
Okay. Okay.
Answer
Okay.
this.
And there is a
Because
last.
wherever there is a scope of optimization, search
Okay.
algorithm, we
Okay.
can use genetic algorithm. But I don't know. I mean, steganography means whatever I know as per my general idea, that steganography means hiding something in the image or video or
Yes. Yes.
somewhere.
Yes.
So if we want to search a particular location where from where the the finding out the location becomes difficult, if we want to do that, so there can be, so there is a search kind of thing to find out the locations where we want to hide that, so there can be used genetic algorithm.
Okay. And there is another question. How can we optimize the architecture of deep learning classifier using genetic algorithm?
So that I have discussed, that the weight can be optimized, the topology of the network can be optimized. So how many hidden layers, how many how many layers, how many nodes in a particular layer should be there. So those things are there in neural networks, and that can be tuned, the weights, those things, so that those things can be done by using some optimization. But these things are very much time intensive. Actually finding out the optimal topography of a particular topology of a particular network is really difficult and time consuming matter.
Okay, and there is a last question from audience. Describe the role of learning rate in gradient descent optimization.
Yes, learning rate plays an important role, because initially from starting from a random location to going towards the optimal minimum or maximum position, we need to take you need to take some steps from x1 to x2, from x2 to x3. So here actually x1 equals to x naught minus, if it is a minimization problem, minus the learning rate with the gradient value. So the learning rate initially considered as a large value, suppose in between 0 to 0 to 2, or 0 to 0.2, or 0 to 0.3, in this kind. So initially we take large step, and on the verge of completion we consider small values, because not to skip the original the optimal value. So initially, or we can linearly decrease the value. So initially we can consider higher value, and eventually we consider very less value, just to converge properly. That's the thing.
Okay, Dr. Mukhopadhyay, your expertise and willingness to share your knowledge with us today have been truly invaluable. On behalf of everyone present, I extend our sincere thanks for your time, dedication, and invaluable contribution to the discussion. So we are going to close this session. Very thank you. Thank you very much.
I'm also thankful to Saurabh sir and all other organizers, and Dr. Shantanu Modok, Madam Devashree Sarkar, everyone for inviting me and
Thank you. Thank
giving me
you.
the opportunity to share my, whatever this idea about genetic algorithm, all those things. So I'll be very much more thankful if participants email me for further discussion, or if they share their suggestions. So those things is
This is
always
this is this is
welcome.
incredible. Actually, this is incredible. You are also telling about to share their actual inquiries or their ideas with you. That's a
Yes,
good
yes.
approach. Okay.
Then only these kind of lecture series has become successful. When
Yes,
collaboration
seriously. Yeah,
happens,
yeah.
then only these
This is
things happen.
right. Actually, this is right. Okay. Thank
This
you.
this
Thank you.
the journey has started. It should not
Okay.
be ended right now. It should be continued.
Yes, yes.
And I
This
will
is a
be more
collaboration
happy.
approach. Actually, this is a collaboration approach. We need all kind of support from all of you. No? All of us actually.
Yes, thanks a lot.
Thanks.
After COVID, we are still going on in online mode. It will be better if you organize in physical events, and then we can come and participants also come, and
Okay.
face-to-face discussions can happen.
We will
That is good.
try to do that. Dr. Mukhopadhyay and Dr. Shantanu Modak sir is also there. Okay, he
Yes.
will also try to do that. Okay, so we are very much thankful to you, and we bring this session to close. I would like to extend my appreciation to all our audience for their active participation and engagement, and your enthusiasm and curiosity have been made this discussion truly memorable. Thank you once again to the speaker, our speaker, Dr. Mukhopadhyay, Dr. Shantanu Modak, Mrs. Devashree Sarkar. Thank you all of you for your contribution today to conversation. Let's continue to explore, learn, and grow together. Wishing everyone wonderful day ahead. Until next time, take care and stay curious. Thank
Thank you,
you.
sir. Thanks,
Thank you.
thanks everyone.
Thank you.
Bye.
Thank you.
Yes.
Thank you. Bye.